Hello, guys. Welcome to my seventh episode of Love the Byte series. My name is Samuel Kamochu, a telecoms and a software engineer. I'm also the co-founder and the lead paysetter at Meliora. In this episode, my objective is to help you appreciate how a computer executes a program. Allow me to start with the definition of a computer. And a computer is an electronic device for processing and storing data, typically in binary form, according to instructions given to it in a variable program. So there are three parts: electronic device. This means that a computer is made up of electronic circuitry that is responsible for processing information and system control. The basic function is to process and store data. So within the computer, we can move data, we can carry out mathematical functions. This includes arithmetic operations, adding, subtracting, multiplying, and dividing, logical operations, comparison of numbers less than, greater than, equals. All those things are possible within the computer. And this data is in binary form. And this is something that we looked at in a previous episode. So in case you haven't watched the episode, you can go back and look for why a computer uses binary. And the last part is a variable program. So a computer executes instructions. And these instructions are written by a programmer. And this is what we call a program. And that program is what is executed on the computer. The reason why it's variable is because a computer is not created to execute a specific program. It executes any program as long as the instructions are supported by the computer. Now that we know what a computer is, we'll go inside the computer and we look at a hypothetical computer called Natujenge computer. This is not a real computer, but it will help you appreciate some of the key concepts that we're looking at. So this is based on a von Neumann architecture. Von Neumann was a guy who came up with an architecture for a computer. So in the computer, we have the central processing unit. This is where all the processing happens within the computer. And we have also random access memory, or sometimes we call it memory or RAM. And this is where we store data that is being accessed and processed by the processor. Then we also have storage. This is where we store data permanently. So in case you want to shut down a computer, whatever is stored in memory is lost, but whatever you store within the hard disk or the solid state device, you're able to recover it after the computer is restarted. Then a computer comes with a lot of input and output device. So we have a lot of input device. I'll just mention a few. We have a keyboard is an input device. A microphone is an input device. A scanner is an input device. The output device, we have the monitor. We have things like the printer, and you have things like the speaker. So all those are output devices. Now there is another key component called the computer system bus. And the computer system bus is basically a group of wires that are meant to transfer data from one component to the other. So all these components communicate with each other through the bus. So CPU cannot access the memory directly. It has to go through the bus. And the same case for I/O devices. So if there is any data to be sent out to the hard disk, it has to go through the bus. So in the bus, we have three types of buses, and the first one is data bus. We also have address bus and control bus. For you to understand what each of them does, I'll use an example where the CPU wants to read data from memory. So memory, each location is given an address. So let's say we have data that is supposed to be loaded from memory location 27. So when you want to read data from location 27 from the memory to the CPU, so the CPU will instruct, we'll power up the wires in the bus, and the address bar will be powered to represent 27, and the control bus will be wired to indicate that we are reading, And once that is given, that instruction is given, and of course, the control bus will also indicate that we are reading from memory. And once that instruction is given, then the data that is in memory will be loaded into the data bus. And once it's loaded into the data bus, then the CPU will be able to read the data and copy it into the internal storage space. So that way, we've seen how the data bus is used to transfer the data. The address bar is used to specify the address, and the control bus is used to give instructions on what we are doing, whether we are reading, whether we are writing, and many other functions that the control bus offers. So now that we know that, allow me to get into the inside of the CPU. So you said that data is being loaded into the CPU. So the control unit is the one that is responsible for the control. So it's the one that is able to instruct each and every component on what to do and activate the right circuitry for the execution of the various functions. So then we also have the ALU inside the CPU. The ALU is basically the arithmetic and the logic unit. All the mathematical functions happen here. So inside here, you'll find things called the adders or the full adders, the subtractors, multipliers, and dividers. So that's electronic circuitry that is able to do mathematical function. But as the CPU works on this data, our CPU requires to store the data that is being worked on. So if you're multiplying two numbers, those two numbers must be within stored within a storage space within the CPU. In the same case, the instruction that is being executed for the control unit to figure out what needs to be done, that data needs to be stored inside the CPU. So the CPU has internal storage, and that storage, we call it registers. So we have different types of registers used for different things, but remember, a register is just used to store data. So I'll deal with three types of register, and the first one I'll call it the program counter. So the program counter is a storage space or a register that is used to keep track of the instruction that the instruction number that we are executing. So in case we have a program that has 5 instructions, so the program counter keeps track of which instruction we are currently executing, the number that is. Now the instruction register, this one stores the instruction that is to be executed by the CPU. So if you're adding two numbers, first the instruction has to be loaded inside the register, and then the control unit will figure out what to be done for us to execute. Now, once we have the instruction and we already know which number of the instruction we are executing, the next thing is the data. So we have data registers, and in my case, I have 2 data registers. So these registers store the data to be worked on by the CPU. So if you want to add 2 numbers, the 2 numbers will be stored in register A and B, and the adder in the ALU will actually do the computation based on the instruction from the control unit. So that typically gives you what happens inside the CPU. So for us to load data inside the CPU, it has to come from memory. But as computers have evolved, the CPU is super fast, and the memory has not kept up with the pace of the CPU evolution. So what has happened is we've introduced a new component called a cache, and the cache is also a storage, same technology as registers or RAM, but it's used to store data that is closer to the CPU. So what happens is, in case you need to read data from memory, the data is loaded into the cache. If the CPU needs to load that data again, it checks in the cache. If it doesn't find it, it goes to memory. So that means that if the CPU is able to get data from the cache, the time of processing will be greatly reduced. So this is the space of the cache within the CPU, just to ensure that there is faster access to data that is in memory. So of course, the cache has a way of synchronizing the data back to the memory once the changes have been made. Now that you know how the CPU works internally, I'll just look at a few memory facts. And the first thing is, both the program and the data manipulated by the program are stored in memory. So we've seen that we have data registers that store data that is loaded from memory. And we also have instruction register, which stores the instruction, which is also loaded from memory. So the program code, these are the instructions, and the data, both of them are stored in memory. So each memory location stores 8 bits or a byte according to the modern day computer. And this is something that you need to remember. So, and of course, this is another nice fact to remind you that with a 32-bit address bus, we have about 4 giga address locations possible, and each location stores a byte. So that means that you can only access a maximum of 4 GB when you use a 32-bit address. I'm sure this is something that you watched in a previous episode. So now that we know how a computer works, we know what the components that are involved in the execution of a program. So all we need now to know is how does a computer execute a program. So I have a sample Java code. This is one instruction or one statement where we are looking at 3 variables, C, A, and B. In this case, my assumption is that the A, which is the variable, is mapped to the memory location 21 that already has value 5. Remember, this is just a simple instruction. Before it, there are other instructions, but for simplicity's sake, we are not going to look at what happens before and after. So we have variable B points to a location 22 in memory, and the value in that location is 6. And then variable C points to a location in memory that is not set at the moment, or it is set to null, nothing, or 0. Now, every processor comes with possible instructions. So when we say programmers write programs, it means that those programs, for them to be executed on a processor, they must use instructions that are supported by that processor. So the instructions are finite, and that's why we talk of a finite set of instruction. And in this hypothetical processor, we have 3 instructions that we're going to cover. Of course, a processor has more instruction, and the manufacturer has a big document that is able to specify all the possible instructions that are supported within that processor. So in our case, we have the load, and the work of the load is basically an instruction to load data from a certain memory location and to a certain register. So you have to specify the location and the register. Store is now moving data out of the CPU to memory. So we have the register, which you want to move data from, and the memory location that you want to send the data to. Then you have add. Add is now a command that is able to activate the ALU circuitry, and its work is to add 2 numbers, and you have to specify the registers, the 2 registers, 1 and 2. Now, each of the operation, although we are using human readable words, each operation has a code, a numeric code. So we can have the load is 1, and this is in hexadecimal, store is 2, and add is 3. So a processor can come with so many operations, and each of the operation has to be given a code. Now, this processor, it's modeled based on reduced instruction set computer. So basically, this is something that you can cover on your own, but the basic idea of reduced instruction set computer is you have very granular or small instructions like, load, store, add. While complex instruction set computer, they deal with one command that is complex. Maybe adding, you just say add, then you specify the memory location and memory location B. That means that for you to add, you don't need to load and store. You basically need to specify the parameters in one command, which is a complex command. So you can read more on RISC and CISC, but I hope this gives you a good starting point. Now that you know a code and we have seen the processor, now we are going to look at how our Java code can be translated into the code that can be executed on the machine. So there are 2 sets of codes that I have written there. So the first one is the assembly code equivalent, and I've also provided the machine code equivalent. So the assembly code is we write the code as humans, but now we specify things like the memory using the keywords or the mnemonics that are given there. So the first thing is in our instruction C is equals to A plus B, we're going to load data from memory location 21. We already know that A points to 21, and we put it in register A. Then we load the data in memory location 22, and we load it in register B. And please note that the A and B here, they're just, it's just coincidence. The variables could have different names, but the registers, we know we have register A and B. And then after that, once the data is in the registers, we can tell the CPU to add the two numbers in register A and B. And then once the addition has happened, then we will tell the CPU to store the data in location 23. And those 4 instructions basically represent the one Java instruction that we have seen. So in machine, basically the mnemonics are replaced with the codes. So you can, instead of register A, you assume that every register has a number. So register 3 is register A, and register 4 is register B, and register 1 is the program counter, and register 2 is the instruction register. So you can see that we are moving, the first instruction is load 01 from 21 into 03, the register. And then we load 01 again, 22 from location 22 into register 4. And then we do add the two numbers. And then finally we do store the number from register A into the location 23. So what you can notice that the add command instructs the ALU to add the two numbers, and the answer is stored in register A, and that's where our program stores the value in A to memory 23. So assembly code and machine code, they are similar. One line of assembly code is translated to one line of machine code. And this is because the assembly code and the machine code, they are very low level. Only that assembly code, we write it with human readable. We write it with mnemonics instead of numbers. So I hope that helps you appreciate what happens. But for me to close, I need to show you, to demonstrate how this will work with our hypothetical computer. So the first thing is we have the CPU and the registers, the program counter, the instruction register A and B. And the memory, we have the whole program stored there. And we also have the data, which we say that location 21 stores 5, 22 stores 6, and 23 has 0. So we are reading, the x-axis, the y-axis, then the x-axis. So in this case, the first thing is to load the first instruction. So we are loading the first instruction and we store it in the instruction register. That process is called fetch. And then the next step is to decode. Decode is the control unit figuring out what this instruction is all about. And in this case, we're supposed to read data from memory. So what the control unit does is that it wires the address, the bus. So the control unit will say we are reading, and on the control bus, we will send a read instruction. And then we'll say in the address bus, we are reading 21, location 21. And in the data bus, we expect 5 to be loaded. And that's when now we get the execution. So once the execution has happened, the data is loaded into register A, which is 5. Now, after that, we increment the program counter in readiness for the next instruction. So once we move to the next instruction, please note that the register A already have 5, and the instruction register has the data that we previously had in the last cycle. So the first step is fetch. So once we fetch, we get a new instruction here. Then after fetching, we decode. Once we decode, we are supposed to know that we are loading data from this location here. So the execute is essentially loading the data, and that happens using the computer system bus, which we've already covered. Then after that, we increment in readiness for the next instruction, which is now the mathematical instruction. And we fetch, we get an add, we put it in the instruction register, We decode, we figure out that you're supposed to add two numbers. In this case, instead of instructing the system bus, we are going to instruct the ALU to invoke the addition circuitry. And it will invoke the addition circuitry, taking the data from register A and B, add it, and once it has added it, it will store the data in register A. So the execution will basically result into 5 plus 6 being saved as 11 in register A. Once that is done, we'll increment the counter again in readiness for the next cycle. And this is now the last instruction where we fetch, and our work is to store the data. So what will happen is we will fetch, we decode, and we figure out that now we want to store the data into location 23 here. So what will happen is the control unit will tell the control bus we are writing, and then it will write on the address bus, it will indicate 23, and on the data bus, it's going to power up our wires to represent 11. And through that, the data will be moved into memory, and that's now the execution. So then after that, we've come to the end of the program. And by the end of the program, the location A, which is 21, has 5. B, actually A has 5, yes. B has 6, and C has 11. And we've successfully managed to add two numbers from memory and store the answer in memory. So in a nutshell, that's how a computer executes the program. And that brings me to the end of this episode. But before I finish, I know some of you might be asking, why is this important? So all programs you write have to follow this cycle. Whether you're doing styling, CSS styling and all that, it has to follow this cycle. So it's good that you appreciate that, because it helps you make better decisions. Now with this knowledge, you have the basic knowledge to optimize your program or the application, to utilize the resources wisely, so you can figure out what you need to do so that you don't waste a lot of memory and resources within the computer or the CPU type. Then the other thing is, this prepares you for handling complex topics such as concurrency. So we will talk about, that caching and how it complicates our life when you're dealing with multi-threading. And this, I believe, gives you a good genesis, a good starting point for such topics. Then it makes you a better programmer. If you know what happens behind the scenes, it is always a good thing as a programmer. And if this sounds interesting to you, or you believe that this content could be beneficial to someone else, please share with them, and feel free to like, comment, and subscribe. Thank you very much, and see you again in the next episode.